let's get on now to talking about where that isotope variation comes from and why. Turi alluded to some of these things, but let's just remind ourselves that when we start thinking about variation in the isotope composition of water, and particularly these three isotopologues of water over here, we're really interested that when we use different isotopes within the isotopologue of water that we're interested in, H or D, 16O or 18O, those are going to have potentially different bond strengths depending on what the mass of that isotope is. So as you substitute in a heavier isotope, whether that's deuterium or O18, you're going to change the strength at which the bond to either the hydrogen or the oxygen in that pair is formed, and consequently how easy that bond is to break. So this is our first clue into why different isotopologues of water might lead to different fractionation effects. The bond strengths are going to be different. Those bonded to light isotopes break more easily than those bonded to heavier isotopes. Right there is one of our rules, and one of the things that leads to the variation that we see in everything we're measuring, not just water, but all the other kinds of substances that we're going to be working on and thinking about during the course here. Vibrational frequencies. Remember, every molecule vibrates, you know? And if you're bonded as a molecule to lighter isotopes, your vibrational frequencies are actually more rapid. You have more kinetic energy, they're more, and so they break more easily also because they're moving more. So depending on who your isotope partner is, that's going to change your vibrational frequency. That leads to differences in the kinetic energy of the bond strengths and consequently how easily or how strong those bonds are. So that's one of those chemical principles that we have to keep in mind. And of course that means that bonds to lighter isotopes break more easily, which we said already. Mass differences is the other thing, of course, that we have to keep in mind. I listed the masses of our three most important isotopum logs over there. Those mass differences are going to lead to not only differences in bond strength, but how water moves between those pools and the fluxes that are influencing those pools. All right? And a heavier isotopologue of water is not going to move as quickly as a lighter one. It's not going to evaporate as easily as a heavier one. So we have to keep in mind that as we change the mass, we change the behavior, just like us, right? It's pretty simple. The analogy is the same, right? And so water behaves in that same way, and that's going to lead to isotope separations between the substrate and the product that's formed from that substrate, depending on what the masses actually are. So bond strength and masses are leading to this isotope variation that we care about. And again, this is not unique to water. You know, Jed's going to talk about this with nitrogen. You know, Jim's going to talk about it with carbon tomorrow. So this is just a principle that we need to keep in our head whenever we start thinking about any kind of an isotope, right there. And then, of course, with respect to fractionation, there's some flavors of fractionation. We've already alluded to these. One called equilibrium or bidirectional, and then kinetic or unidirectional reactions. And those are going to lead to different isotope effects. And then once again, this is the mantra that all of you have to have tattooed on the inside of your eyelids before you leave Salt Lake City. Lower temperatures, greater isotope effects. Temperature is going to be something, particularly with water, that we always have to be paying attention to. We don't live on an isothermal planet, right? And so whenever we do anything with water, we're generally also changing temperature. And consequently, you're changing the fractionation factor. So this is something we constantly have to pay attention to, is changes in temperature change the game here. Even though it might be an equilibrium or a kinetic isotope effect, it's going to have a temperature effect thrown in there.
And is the physics of that just like at higher temperatures there's more energy in the system, so like every reaction can happen?
Indeed, yeah. If you want to kind of boil it down in kind of the most straightforward terms, that's right, exactly. There's a little more under the hood there, but all right. So let's talk about then the types of fractionation. And I'm going to go through this quickly because these are things that Turi kind of touched on, but I want to kind of just remind us. So equilibrium reactions, we already talked about that when we were talking about that cartoon. Complete back reactions are possible. So evaporation, condensation. That's a nice equilibrium reaction. Really easy to understand. It can move back and forth. The product that's formed can go right back into the substrate that it came from. And so the only thing that you have to worry about is when that phase change takes place, when you create a vapor from the liquid, you're still going to get an isotope effect. But as long as they're in equilibrium, we only have to pay attention to one isotope fractionation value, the equilibrium value between the liquid phase and the vapor that formed from it. All right? Reactant and product then are offset by a certain isotope value, and again, that's going to be temperature dependent. And so we characterize that with our fractionation factor alpha. And I'm going to frustrate you during this lecture, so I've given a disclaimer up here. I'm going to be working back and forth between alpha and enrichment values a lot. Whenever you start working with water, you work with both of them, and I just reminded you what Turi showed us yesterday. Mostly when you're working with enrichment values, you're just putting in per mil notation, all right? Instead of working in the third decimal place, you're actually working with bigger numbers. It's the same thing. It's just different ways of expressing it, all right? Then we have a second class of fractionation factors. These are the kinetic ones, and these are the ones where we have to think about the fact that not all of the product that we formed, the vapor from the liquid, all right, is going to come back. So we have incomplete or maybe even no back reaction. Like in the case of biosynthesis. When you make a sugar out of CO2 and water during photosynthesis, we're not getting CO2 and water back for a while, right? And so many of those are kinetic reactions. They're one way. They're not bidirectional. And so that's going to be an additional isotope effect, all right, that you have to pay attention to. So that's a different class, which we call the kinetic isotope effect. If you happen to have a closed system, they are going to evolve together. So do a thought experiment with me here. I'm a glass of water. You put a bell jar over the top of me, and I'm going to evaporate, all right? But the evaporite coming out of me as a glass of water isn't going to go anywhere because I'm closed. I'm in a closed system here. So there's going to be an offset between me as the water and the vapor that forms from me. And I might boil away, all of me, into vapor, right? God, would that be cool? Right? I am from Berkeley. You have to realize that. But as long as it's a closed system and I'm not losing anything from that bell jar's over it, it's just the product and the substrate that forms from it, they're going to evolve together. All right? They're going to be kind of a constant offset value. All right? Now, when we go to an open system, like, oh yeah, planet Earth, all right, we often then have a lot of things that, at least in our time and place, we're losing. We take the bell jar off, and some of the product that we create goes away. Right? Now, really, in the end, Earth is a closed system. We're going to get most everything back. Most of the water, of course, that evaporates and moves around the planet, we're going to get it all back eventually. But it may go sit in a glacier for, 50,000 years. And then eventually melt and get back into the ocean. We'll get it back. We'll get all the isotopes back, right? But we may never see it. So in that sense, it seems like an open system. Some of what we create is going away. It's leaving the system. That's an additional isotope effect, all right? Because you're creating that product, but you're not keeping it all in equilibrium with the substrate that it formed from. So those are additional isotope effects in the hydrologic system that we really have to pay attention to. And a lot of you who are biogeochemists in this room know that that's something you're going to have to pay attention to, because you're not, some things are on kind of a one-way trip. They're going out of the system. They might get used by an organism, or they might volatilize. So these open system effects are something that you see a lot. Now, when you're talking about water, many times it will get a little confusing. Sometimes you'll hear diffusive or transport fractionation, all right? It is essentially kinetic fractionation, but it's along a concentration gradient, all right? And so people, when they're talking about water, will use diffusive fractionation and kinetic fractionation interchangeably. And mostly it's because when you go from the ocean, 100% water, all right, to something less than 100% water, the vapor that's forming out of that ocean, it's diffusing away. There's an isotope effect associated with that, and it may be leaving the system. It's on its trip from Hawaii to Utah, right? And many times people will talk about that as a diffusive fractionation, all right? You also hear this used sometimes when people are talking about how minerals that are formed out of the mantle on the Earth are kind of on a one-way trip, and they're diffusing from a high concentration in the mantle to a lower concentration in the mineral that's formed from that mantle. You'll also see sometimes that called transport or diffusive fractionation. Don't get confused by it. It's really kinetic fractionation. It just has a different label associated with it. It gets used in the water world a lot, all right? So you'll hear this. But just don't get confused by it. I wanted to make sure that we just kind of highlighted that. Did you have a question? Okay. All right. Now, let's put some real examples behind these different fractionations. So exchange or equilibrium fractionation, so that's where we get, of course, liquid droplet formation out of a cloud. So we create vapor, cloud, we get condensation back out of it, equilibrium effect. Easy. That was a pretty easy one to understand. Evaporation into the boundary layer. What's the boundary layer? Okay, good, we're getting there. It's that zone above any surface has a boundary layer, right? Unless we blow it away with wind or something like that. And the boundary layer over the ocean, which covers 70% of our planet, is that little zone right above the liquid phase that's at 100% relative humidity. It's in touch with the liquid phase, but it's vapor. But it's saturated vapor. It's at 100% relative humidity. It's a ginormous skin, right? It covers 70% of our planet. So it's a big boundary layer. And there's an equilibrium isotope effect that takes place in that boundary layer.
Would that just be like just a few millimeters?
It is, indeed. Bingo. You're absolutely right. And sometimes it goes away if we put wind on it, right? Exactly. Point taken. Kinetic. We just talked about kinetic. So when we precipitate minerals out of the mantle or out of magma, that's a kinetic isotope effect. That's a pretty easy one to understand. Biosynthesis. Jim's going to get into talking about carbon tomorrow, and you're going to realize that most of the isotope effects Jim's going to talk about are kinetic isotope effects. They're on kind of a one-way trip. They're enzyme mediated. You're creating carbon, combining it with water, making sugar, right? That's a kinetic isotope effect.
So when you're talking about a boundary layer of a leaf, you're talking about also where it's at 100% RH?
Yeah, and it can be, and that's submillimeter, right?
Yeah.
And of course, the smaller the leaf, the smaller that boundary layer.
So the boundary layer always is defined by 100% relative.
That's right. That's exactly right. Yeah, and it's usually unstirred air. It's usually, but sometimes it can be so small that it's almost impossible to measure. All right.
Sorry, I'm actually confused about that. Because like in energy balance stuff, the boundary layer, like above at the landscape level above the tropical forest, is like dozens of meters sometimes.
Okay.
And is that like a different?
It is.
type of boundary
It's
layer?
defined in a different way. We're defining it as that layer that's at 100. It's a saturated atmosphere. Many times, and Dave Bowling will say this when he comes in and lectures to you guys, he'll talk about the ecosystem boundary layer. So this boundary layer, like you say, that's kind of above a forest where the turbulence and the mixing is very different than just above that. That's still called a boundary layer, but it's not defined the same way here. Right, exactly. So the eddy flux community doesn't define the boundary layer the same. So when Dave comes back and lectures, make him define his boundary layer for you. All right? Say, we heard one definition. What's yours? All right? All right. And then we already talked about the diffusional or transport. Okay? And again, I just want to make sure that we understand that these diffusion or equilibrium effects are not mutually exclusive. And when it comes to water, they're both going on. And you'll see that that's manifests itself when we start looking at global meteoric waters over the planet. Now, when it comes to looking at the equilibrium fractionation factor, let's talk about just equilibrium fractionation right now. And that vapor-liquid exchange, this is where we start looking at I've expressed these in epsilon values, which again, this is mostly just expressing this in per mil notation. I like it because it's just easier for me to pay attention to. But here I just want to point out two things. First of all, the temperature effect. Look at the magnitude of the difference at 20 degrees versus 80 degrees up here in either the hydrogen or the oxygen fractionation factor. Much, much larger at cooler temperatures. For hydrogen, look at that. A 74 per mil change between the liquid phase and the vapor that formed from it at 20 degrees C. A 38 per mil change if we raise that temperature by 60 degrees. Big effects. Temperature plays a huge role here. This is why we have to pay attention to it. And we can do that for hydrogen, we can do it for oxygen, and then we can express them as a ratio here. And this is the thing that the second point I want to point out here is that when we start looking at either at 20 or 80, or if we express it in terms of mass differences, this number 8 comes up over and over again, no matter how we kind of look at this. And this is really just like the coolest thing ever, right? Because this starts to show us that maybe we can look at all kinds of waters at all kinds of temperatures, and there's going to be a rule there. Something's going to hover around 8. Let's talk a little bit about how that plays out in the hydrologic system, all right? And how it plays out is this number 8 here basically is, as I say here, is it's kind of getting you to think a little bit about the magnitude of the isotopic effect differences between hydrogen and oxygen. And they're 8 times larger for hydrogen than they are for oxygen, all right? And again, this is assuming that we have only an equilibrium fractionation offset at whatever temperature we happen to be looking at here, all right? But there's one thing we need to pay attention to. Oops, before I go on to that, oops, go back. That means that anything that expresses itself as kind of this ratio of 8 is an equilibrium factor, all right? And when we go look at this thing called the global meteoric water line here in a few minutes, you're going to see that number come back to us. And that's really cool because it means that some of what we understand about precipitation on our planet, if we start seeing this number 8, and you'll see it's going to be the slope of the line between hydrogen and oxygen, all right, for all the precipits across planet Earth, it's the slope of 8. And it says, that's an equilibrium process. The slope of that line has got to be an equilibrium process. But you'll see that the intercept of that line is not going to be 0. All right? And that means that it's not all about equilibrium. There's going to be some other things going on. So when we start looking at these equilibrium fractionation factors, that starts to give us a little bit of insight into the processes that dominate influencing the isotope variation of water on the planet, but they're not the whole story. All right?